So last time we talked about we say, let's get deeper inside the material and try to develop a certain knowledge that help us to distinguish between atoms, right? And we end up saying that, well, we can differentiate between atoms in terms of their masses, right? Some of them, they have small masses, some of them, they have larger masses. And we know that the only contributor toward the mass of atoms are the protons and the neutrons. And then we get into what's called atomic number, which really depends on the number of protons. And now we will get into the periodic table very quick, very brief. If you want to get more details, you can go to the video that I uploaded to Blackboard. Okay, so the periodic table, so the atoms are not randomly exist in the periodic table. Rather, they are classified in groups with a certain criteria. So if you look at the periodic table, you can find that the rows, they have a different number of quantum numbers. So as you go down, as this number is increasing, right? So 1 to 7. And also, if you look at each group over here, each group, they share the same number of valence electrons. So they have the same number of valence electrons, right? Also, sometimes the properties might have some common properties. In each group, they might have certain common properties. Now, if you look to the far left in the periodic table, okay, you're going to find electrons, the elements here, they are willing to give up electrons. The reason behind that, because let's give a closer look to this atom that will be located at this square over here, right? So that will have extra electrons. If that atom is able to get rid of that electron, it will have the electronic configuration of this the elements over here, right? So that means 2s1, if it's get rid of the 2s1, it's going to left with the 1s2, right? So it will have the electronic configuration of the inert gas. So the elements that exist to the left of the periodic table, those elements will do their best in order to give up electrons, to get rid of those electrons in order to assume the electronic configuration of the inert gas. However, as you go to the right in the periodic table, you go far to the right here, right? So there is, for example, let's take this example. Whatever element that's going to exist at this square, right? It's missing only one electron in order to get the electronic configuration of the inert gas, right? So they will do their best in order to accept electrons. Now, typically they use something called electronegativity or electropositivity. Electronegativity, that means the tendency of those atoms to accept electrons, right? So that means atom with higher tendency to accept electrons, it might mean it has higher electronegativity. Now, let's try to plug those numbers on the periodic table, right? The numbers of electronegativity, right? So we can have all these elements with their electronegativity values, and you can see that the electronegativity value is increasing as you go from left to right? So that means the tendency of those elements to accept electrons will be higher, right? Great. So this is very important because as you go further to discuss the atomic bonding that can exist between atoms, electronegativity is going to play a major role in determining what kind of bond you will have, and also that what kind of bond will determine what kind of properties the material also might have. Okay, so if you look at if you look at the periodic table, the atoms the elements are classified in a certain way, so they are not randomly arranged in the periodic table. So we have, for example, in the middle we have what's called transition metals, where all these metals over here, the d orbitals are partially filled, so it's not completely filled. Okay. And also you notice that if you go to this figure over here, you notice that most of the elements in the periodic tables are metals. Most of the elements are metals, right? And then you hear toward the right, you have non-metals, and some of them, they have this mixed character of metal and non-metal. It's called intermediate, okay? For example, metals are electrically conductive, right? But and non-metal are not electrically conductive. Silicon have this mixed character as well as a semiconductor material, right? Okay, wonderful. That will help us to move to the second step, where we're going to talk about, okay, now I can differentiate between different atoms, their masses, where I can find them in the periodic table, how the periodic table is representing those elements, how they are correlating to each other. Well, electronegativity is increasing from left to right. Electropositivity is increasing from right to left, right? From right to left, the electropositivity is increasing. Great. Now, how can we use this knowledge now to move one step further and we say, okay, what's going to happen now if a certain element in this periodic table start to get into a relation with another element? Okay, what kind of relation can exist? What kind, we call this relation bonding? What kind of bonding can exist? And this is very, very important, because really it's going to determine many of the characteristics of the material. Let me remind you last time that when we say that the inert gases, they are stable. Okay, please, I want to say something. Just keep it in your mind throughout the semester. Okay, I want to say something that please keep it in your mind throughout the semester, which is, the inert gases, the material in general, they're trying to, they would like to have the possible state of energy, that's the minimum possible state of energy. Right? What does it mean? What does that mean? The material would like to have minimum energy. Why? Because as the energy increases, if the energy of the material increases, the material will not be stable. The material would like to get into any reaction that will help us to minimize its energy. Okay? Now, that can tell us why the inert gases, they are inert. They don't want to get into any reaction because their energy is, those kind of gases, they have the minimum possible state of energy. Hello? They cannot minimize the energy further. However, if you look at the rest of the elements here in the periodic table, no, whether some of them would like to give up electrons, some of them would like to accept electrons in order to assume the electronic configuration of the inert gases in order to minimize their energy. Right? This is why the elements will get into reactions in order to minimize their energy. If that reaction will increase their energy, they will not get into that reaction. So they will not form any bond with a certain material. Right? Okay, great. So that will take me to what we call the atomic bonding. Okay, we can classify the atomic bonding into two types. We can classify the atomic bonding into two types. Primary bonding, and we have the secondary bonding. Okay, when we talk about primary bonding, the primary bonding is more stronger, right? And there are three different types. We have the ionic, we have the covalent, we have the metallic. The motivation is to minimize the energy of the two elements, of the two atoms, right? So the two atoms will have covalent if that will reduce their energy. The two atoms will have ionic if that's going to reduce their energy. The two atoms will have metallic if that's going to reduce their energy. But before we get deeper, I would like to bring to your attention that we are talking about bonding between atoms. We are not talking about bonding between molecules. Now, if you, I'm sure most of you now today in the morning, maybe you boil the water now to prepare your tea. Now imagine you left that the heater, okay, on, and the water keep boiling up. What's going to happen, right? The water going to evaporate. Now, water is evaporating because you're breaking bonds. But that bond that you're breaking, you're not breaking the bonds between the H and the O inside the molecule, right? It's because the water molecule has H2O. You're breaking the bonds between the H2O molecule and the H2O molecule, right? That's easy to be broken, right? When you heat it up, so this is what you're breaking. You're not breaking the bonds between the H and the O inside the molecule, right? Okay, so now the atomic bonding, we are talking about the bonds that exist between the atoms inside the molecule. For example, H2O, we're going to talk about the type of bonding that connecting the oxygen with the hydrogen inside the molecule, right? This is called intramolecular bonding. Okay? I-N-T-R-A. If we are talking about the bonding between the molecules, we call it intermolecular. That means I-T-E-R, intermolecular, right? So here we're talking about the intramolecular bonding, okay? So so inside the molecule. This is very important, okay? To pay attention to this as we go further. Okay, great. Now, if you would like to have a table, right? A table of different group of material, okay? We want to differentiate, we want to compare between the what's called bonding energy. Why we care about bonding energy? Because we want to know how much energy we need in order to break a certain bond, right? That's going to tell us how much strong is that bond. So if you look at this group of material on top of here, well, the bonding energy is very high, right? So bonding energy is very high, and that is reflected on the melting temperature. You need higher temperature in order to melt to break bonds of those kind of material, right? Okay, great. Now, if you go to other group of material, you notice that the bonding energy here is decreasing, and it's decreasing. I keep decreasing, right? And similarly, if the bonding energy, if it's weak, that means it's easily to break the bonds, okay? Now, notice here H2O, okay? H2O has a bonding energy that's 51 and 51. That means this is why the melting temperature is around 0 Celsius. Now, this is for the bonding energy between the molecules, this is what, this is between the molecules. This is called hydrogen bonding A, and if you look here, they say values for van der Waals and hydrogen bonds are energy between molecules or atoms, intermolecular, okay? Intermolecular, that means between the molecules, okay? So that means this 51 is not representing the bonding energy between the H and O inside the molecule. I hope that it's clear right now. But great, so that means as the bonding energy is very strong, it's going to be very difficult to break the bonds. Okay, great. Now imagine that you have two atoms, and you want to plot what's going to happen if they are far away and you start to bring them closer to each other. What's going to happen? What kind of forces that might exert on each other, okay? If you have two atoms that far away from each other, they don't see each other. There is no any effect. There is no any impact. However, if you start to bring them closer to each other, right, there will be some attraction force. Why we have attraction force? Because if they will come closer to each other and that's going to minimize their energy, there is something is pulling them toward each other, right? Because that's going to help this atom, that's going to help this atom, right? Which at the end they will minimize their energy. There is something that is attracting them, right? So there's an attraction force between those two atoms, right? And similarly, oppositely, if you bring them very close to each other, you know that each atom has a nucleus, and then around the nucleus we have revolving electrons that we talked about last time, right? So you have a negative charge, okay? And here also you have a nucleus positive charge, and then you have the electrons around the nucleus. If you bring them closer to each other, what's going to happen? The electrons here and the electrons here will try to pull each other, try to repel each other, right? So the electron, they have because negative charge with negative charge, they will repel each other. So that means if you as you bring them closer to each other, there's something that's pushing them toward each other, but then once the electron here will start to overlap with the electron over here, they will repel each other. So you have attraction and you have also repulsion, okay? So you have attractive force, you have also repulsive force, okay? Now what we care about the net force, which is the summation of attractive force plus the repulsive force. This is what we care about at the end of the day. Because at a certain point, there will be some repulsion and some attraction. We want to know what is the resultant of those forces, right? Okay. And if we want to plot this, let's look at this figure over here. You have y-axis, you have the x-axis, right? So the y-axis is representing the forces. The positive force is representing the attractive force. The negative is representing the repulsive. Now let's look at the attraction. And the x-axis is representing the interatomic spacing, how far they are from each other, the atom, right? So if you are here, they are far away from each other, right? And you start to bring them closer to each other, right? You're going to follow the blue curve, right? As you bring them closer to each other, the attractive force is increasing, right? Because if you bring them closer to each other, there is something is motivating that attraction, which really depends on the type of bonding that we're going to talk about in a few minutes, right? But also, if they bring them closer to each other, there's a repulsive force that also is increasing. At a certain point, it's also increasing, and we care about the net of these two forces. So what's going to happen? You got to take the net, which is the red curve, okay? The addition, the summation of these two forces. You notice it's going to go up, and then you're going to go down. Very important to point something here that if you look closely here, right? At a certain point, the net force is going to equal to 0. The net force is going to equal to 0. That means the repulsion plus the attraction will equal each other, right? So at this point, FA going to equals to negative FR. So they are equal in magnitude, opposite in direction, right? So that means at a certain point, whatever is pushing them apart equals to whatever is bringing them closer to each other, right? We call this spacing between them, okay? The spacing between where the F net equals 0, we call it the equilibrium interatomic spacing. The R naught is called equilibrium interatomic spacing, okay? Now, most of the time is convenient to deal with energy rather than forces. Right? So the way that we can do that, we can take the integration of the forces, right? We can have this plot over here, right? Where we have, so when you take the integration, so the repulsive now will come here, okay, positive, and the attraction will come negative. Okay, and the net force, so we need the net energy for these two kind of energies. Okay, you're going to notice that as the atoms are far away from each other, okay, they have a certain energy, the energy between them. As you bring them closer to each other, the two atoms can minimize their energy. So the energy of the system will be lower. So there's something that's telling, come closer to each other. Let's come closer to each other, right? As you bring them more closer until a certain point, okay? And that point is representing the minimum in that curve, right? And then if you bring it more closer, pay attention that this point is corresponding to the F net equals 0, and we call that spacing the equilibrium interatomic spacing. Now, if you bring them more closer to each other, we say now the electron here will start to repel the electron here, so there'll be some repulsion forces. Okay, great. So what's going to happen? Well, what's going to happen, the energy of the system now will increase. Does the material prefer that? No. Well, the atoms would like to come closer to each other now, more to come closer, less than the equilibrium spacing. The answer is no, because that will increase the energy of the system. This why the material, the two atoms will be very happy to have this will come closer to each other with interatomic spacing equal to the equilibrium interatomic spacing R naught. Okay, because that's going to have the minimum energy in this curve. Okay, it's called minimum and that is representing what's called the bonding energy, right? The bonding energy. That means if we have this curve, okay, this curve, okay, you notice that this point has lower minimum energy compared with this one. That means this will be the bonding energy will be higher, right? The more negative you go, the higher is the bonding energy. That means stronger the bonding will be between the two atoms. Okay, great. So again, the two atoms will have a bond when F net equals 0 and when the E net equals to minimum. Common mistake in every semester. The students, when they do the calculation later, okay, as you go in the book, there's an example about this. They consider when there will be bonding when E net equal to 0. That's wrong. E net will not equal 0. Okay, E net will be minimum. What's gonna be gonna equal to 0 is the net force. Okay, so the net force gonna equal to 0. So when F net equals 0, the net energy will be minimum. Okay, and that will be at the equilibrium interatomic spacing. Okay.
دكتور عندي سؤال بس.
Okay, go ahead please.
أنا ما فهمت بس دحين لما التو اتومز يقربوا من بعض هو حيكون فيه يا اتراكت يا ريبلز، بس في الرسمة هنا مكتوب إنه فيه الاثنين.
Yes.
فكيف صار فيه الاثنين؟
So typically دقيقة بس عشان في واحد بيدخل. حسين الأوسيس please contact me after the lecture. طيب حسين الأوسيس. حسين العويسز please contact me after the lecture. طيب back to your question. Who asked the question?
هنا سلطان.
حياك الله يا سلطان.
الله يحييك.
Okay, so Sultan asked a very good question. He said, what's going to happen? His question, what kind of forces we might have if two atoms talk to each other? Well, when two atoms see each other, there will be attractive force that's pulling them toward each other. And that attractive force will depend on the type of bonding that exists between the two atoms. طيب ايش الموtivation? What is the motivation of the attractive forces? In the same time, if they start to come very close to each other, here we have electrons and here you have electrons, right? So what's going to happen? Electrons have negative charges, right, يا سلطان? وهذا الاتومز فيها negative charges. So negative and negative will start to pull each other, they try to push each other away from each other. صح ولا لا? We're going to have repulsive force. صح? So for the two atoms, as they come closer to each other, two forces, two types of forces will take place: the attractive and the repulsive, right? And what we care about the net of the two. واضح يا سلطان؟
واضح شكرا.
حياك الله. Okay, great. So now back to the to this point again. So that means we care about. Can you please mute your mic, and also whoever came here with AA letter, please contact me after the lecture, and also Hassan al-Races. Okay. What else? Okay, great. So that means we care about what's called the energy, the energy of the bonding, what can be found in the as the minimum point in the energy curve. Okay, great. Why
Doctor, I have a question.
Please go ahead.
The minimum, I have a question.
Yes, go ahead.
The minimum point of energy is the maximum attraction energy, correct?
لا. So this is the attractive energy. Okay, it's keep increasing. There is something is motivating the material to come closer. But at the same time, there is a repulsive energy. Okay, the repulsive energy is going to go higher and higher as you bring them closer to each other. Why? Because the electrons will repel each other. We don't care about this. We don't care about this. We care about the net of both of them. And we don't care what's going to happen here later. All what we care about is to identify where is the minimum. واضح؟
اوكي.
دكتور نشاط.
حياك الله تفضل.
الحين
بس سوري قبلك يا خليني اجاوب الاخ اللي قبلك. الاسم الكريم اللي قبلك مين كان؟ مين
سؤال الانرجي؟
حياك الله يا صالح. معلش خليني اكمل لك الاجابه كمان. This is a mathematical plot. طيب we are trying to يعني just to give a certain value of R and to see what is the value of E, whether it's EA, EN, ER. طيب we are giving value of R, right? And trying just to plot. In reality, the atoms will not come closer. طيب not come closer to each other more than this point. خلاص. But this is just a plot to tell you that this is something most probably it's impossible to atoms to come to have a certain energy. طيب واضح؟ واضح يا عنزي؟
But what I was saying is that in the minimum potential energy, there's maximum attraction energy, correct? Or is that even?
So we're not talking about the attraction, maximum of attraction. We're talking about the minimum is correlated not to the maximum of the attraction, it's correlated to the attraction plus the repulsive. And at a certain point, if you do the summation, that will give you the bonding energy. Right?
Okay.
Okay, who's next?
أنا دكتور.
تفضل.
الحين when the net force equals 0, we will have a minimum attractive energy, right? And at this point, the distance between the two atoms will stay the same and bonding will happen. Unless other forces act upon it and will separate them.
Yes. So what's going to happen if you look here, at this point when F net equals 0, طيب, the amount of attraction between them, the amount of the magnitude of the force that's pulling the two atoms together equals to the one that's pushing them away. That means they will stay at a certain position because they cannot go away and they cannot come closer to each other. طيب. They will stay as it is. This is representing the interatomic spacing. That means you, as a foreign from outside, you try to bring them away from each other, or you want to break that bond. That means you have to apply energy. The system will not do that for you. That means you have to apply energy. This is why for us, in order to push the atoms away from each other, push the atoms away from each other, bring them here or there, we have to apply energy. صح? You have to apply energy. Either, for example, if you heat up the material, you're going to let them vibrate until they break that bond. Okay? And then if they break that bond, then there is no connection between them. طيب? Unless they are very close to each other, and then they're gonna break. They're gonna create the bonds again. واضح يا مين سألني؟
واضح دكتور.
طيب, great. طيب, now that's gonna take us to what's called the primary bonding. طيب, primary bonding, the main motivation. So why we are talking about primary bonding? Because that's gonna determine the type of attractive force that we're gonna have. Okay, so the primary bonding will determine what kind of attractive force that can exist inside the material. And the primary bonding depends heavily on the electronegativity, whether they have large difference electronegativity or small difference electronegativity, that determine what kind of bonding we will have. Okay. Now let's start with the ionic type of bonding. I guess most of us are familiar with this ionic type of bonding. Typically, this happens when you have large difference electronegativity. If you look at the periodic table, right? If you look at the periodic table, we're talking about something that is the far left with something in the far right. Okay. In that kind of bonding, the atoms willing to the one in the far left would like to give up electrons, the one in the far right would like to accept electrons, right? Let me remind you with this with the periodic table over here. So the elements that exist here, they're willing to give up electrons. However, the atoms exist here, they're willing to accept electrons, right? So there is high tendency for each one of them to get into a relation with each other in order to minimize their energy. This guy is willing to give electron. Let's say the sodium is willing to give up with electron, and here the chlorine is willing to accept one electron in order to be stable, right? So ionic type of bonding exists when you have this large difference electronegativity, right? So typically happen between metal and non-metal. Now, what's going to happen if the sodium that's unstable will give up the electron? So the sodium ions become positive, right? So become an ion, and then the chlorine will accept that electron and become negative, right? Here we have giving and acceptance. There is no sharing, giving and acceptance. Okay, so now that electron does not belong to the sodium anymore. Now it's belong to the chlorine. Right? Now what's going to happen? You have positive and negative charge ion. So they will. There is something that's going to pull them toward each other, right? There will be Coulombic attraction, right? That Coulombic attraction, what's going to happen? It will try to pull them as closer to each other until a certain point where electrons here and here will overlap, and that will result in repulsion. Right? Okay, great. Now we can say that the attraction energy is a function of the interatomic spacing, right? As you bring them closer to each other, the plot of the attraction. So let's go back here, right? So you notice that an EA is a function of R, right? It's a function of R. So we can plot value of R. We can plot the value of the attraction energy. Similarly for the repulsive. Similarly for the net energy. Right? So EA equals to minus A over R plus B over R to the power N. This is constant, this is constant, okay? And R is the interatomic spacing. A, we can calculate A by using this equation. What is Z? Z is the absolute charge value. For example, for the sodium, what is the absolute charge value of the ion? It's positive 1. For the chlorine, as negative 1. So absolute, so negative 1, it's going to be 1, okay? So Z is representing the absolute charge value. E is a constant called electron charge. Okay, it's a constant number. Here we have 4 by and then permittivity constant, also the constant number. Okay. Now, how we can get the force value from the energy? We do the derivative, right? So if the energy is the integration of the force is the derivative of the energy. So when you do the derivative, it's going to be A over R squared. Okay. So that means also the attractive forces or repulsive forces is a function of the interatomic spacing. Okay, let's give a look here for another example, just to make things much clearer. Now, magnesium oxide. Okay, magnesium has electronic configuration 1s2, 2s2, 2p6, and then 3s2. Okay, we can write it in a different way. We can say all this is representing the neon electronic configuration. Now we have, this is extra, the 3s2, right? So the 3s2s have the neon plus the 3s2. The magnesium will try to do its best in order to get rid of those 2 electrons, right? Now if we look at the oxygen, okay, the oxygen it only needs 2 electrons in order to assume the electronic configuration of the neon, right? So what's going to happen? If you look at the periodic table, magnesium is here 1.3, oxygen 3.5, large difference in electronegativity. That will motivate them to come closer to each other and to form a bond, and that's going to result in ionic bonding between them. Okay, great. We have also many other examples. Okay, sodium chloride, or magnesium oxide, whatever. Okay, most importantly, I would like to bring to your attention that notice that material exists in 3D, not only in 3D. For simplicity here, we're talking about atom with atom, but in 3D, actually, this sodium is surrounded by this chlorine and that and this and that, and something in the back and something in the front. بالتالي, when this sodium is giving its electron, that electron will not go completely to this chlorine. However, that electron will be shared to the all closest surrounded chlorine ions. Okay. So that means the relation, this sodium is not only connected to this chlorine, rather this sodium is connected to all the closest chlorine ions. So that means the ionic bonding is non-directional. So that is not only happening between this atom and this specific atom, rather it's happening between this atom and the closest surrounding, as it's called, non-directional. Okay, non-directional. Okay, so ionic bonding typically has higher, large value for the bonding energy. Typically, you need to apply high amount of heat in order to break the bonds. Okay. Okay, wonderful. The second type is called covalent type of bonding. In the covalent type of bonding, we are sharing electrons. So what's going to happen? They have similar electronegativity. So hydrogen has 1 electron. When you see another hydrogen with 1 electron, so this hydrogen cannot give up its electron and cannot accept 2 electrons. So this hydrogen is willing only it would like to get 2 electrons in order to be stable, right? So it cannot get rid of its electrons. So what's going to happen? They will share the electrons between each other. So these 2 electrons does not belong to this hydrogen. It belongs to the molecule, to both of them, right? So they are sharing. They are not giving. Okay. And since it's sharing, that means whatever electron is there, it belongs to both, to the new partner, okay, and the person himself, right? That means this is happening. This we'll call it directional because it's happening between specific atom and specific atom, right? And even sometimes it's happening with a specific angle. So between this atom and this angle with a specific angle. So between atom and atom with specific angle. Okay? Like in H2O. H2O. What's going to happen in H2O? Let's draw that. So in H2O, you have this hydrogen, right? Okay. Okay. Let's just delete this. And then go here. You have hydrogen, right? And you get the oxygen and then 2 hydrogen, right? This is representing the H2O. Now, the bonding between this oxygen and hydrogen is covalently is a covalent type of bonding. It's covalent type of bonding, right? It's directional with a certain angle between these 2. Okay. Now, again, remember, this is a covalent bonding between the O and H inside the molecule, right? Now, that molecule have a connection with another H2O. We're going to talk about later, inshallah. How these 2 molecules will connect to each other. We're going to talk about it, inshallah, in a few minutes. Hopefully, I can finish this lecture. Okay, so we're going to find some elemental solid like diamond and silicon. Also non-metallic elemental molecules like hydrogen or fluor, whatever. Now, the point here is that this is directional, and we cannot predict the the melting temperature by knowing the covalent bonding, right? Why? Because we can get some of the material like a bismuth. It has low melting temperature, 270. Okay, and then you get into the for example, you have the diamond, and diamonds I guess is around 3,000. Let's see, 3,550. So let's say about 3,000. Okay, so you get something that has covalent bonds around 200 something, and then about 3,000. Okay, although both of them have a covalent type of bonding, so we cannot predict the melting temperature. Right? Some of them are weak, some of them are strong. Right? Okay, the third type of bonding is called metallic. Metallic, they have something very special because it's happening between metals. What's special about it is that now we have this atom and this atom and so all the atoms inside the material, what's going to happen? They have the nucleus inside them, and then around that nucleus you have some electrons, okay, that's very close to the nucleus, right? But the rest of the electrons, so some of them will be around the nucleus, okay, and the rest will be belonging to the material and does not belong to the atom anymore. And that results what's called positive cores. You see positive cores here, the red circle over here, so it's called positive cores. Now inside that positive cores, you have the nucleus and you have the electrons. But why is positive they have electrons? Because the electrons that they have it inside are not enough to shield the positive charge of the nucleus, okay? This is why it has a positive charge. Right? Now the rest of the electrons that used to belong to this atom, now it belongs to the whole material, right? Now, so that means the electrons are free to drift inside the material. We call this sea of electrons. So we have sea of electrons here. Okay? So they're able to drift inside the material, and that's going to tell us why the metals are thermally and electrically conductive material, because electrons can transfer those they can conduct the electricity and also they can conduct the heat. Okay, great. So we have positive cores, and then you have this negative charges that will act as a glue for those positive cores. Why? Because those negative charges surrounding each positive cores, right, will try to shield the positive charge. Okay, whatever is outside those, the negative charge is outside that the free electron will try to shield each positive core. Why? Because otherwise, if they don't do that, what's going to happen? Those positive will try to pull away each other. Sorry, it's going to try to push away each other. So this is why those electrons will be surrounding the core from all the directions, right? Now they call this kind of bonding also non-directional, right? Because this is getting in relation with this another atom, not in a specific angle, right? Rather they are the electrons now of this atom belong to the whole material, right? So in all different directions, it's called non-directional. So among the three different types, we have only one type that is directional, which is the covalent type of bonding. Now sometimes, well not sometimes, in most real materials, you cannot get a pure ionic material, you cannot get a pure covalent material, you cannot get a pure metallic material. Rather, you get a mix of character, of character. For example, you might get a mix of character between covalent and ionic. How that could happen? Well, if you look at the periodic table, if the two elements have not very large, if they have large electrical conductivity, or they have large value of electronegativity, if they have large difference electronegativity, what's going to happen? They'll have ionic character. However, if the difference is smaller and smaller, okay, they will have kind of covalent bonding. That's why it's called covalent ionic character. Okay, how we can quantify this kind of character? We're going to use this equation. Okay, this equation is going to tell us if you plug 1 minus E, if you plug the electronegativity values here, right? You can calculate the character, the ionic character. Let's, before we end this class, let's take this quick example, okay? If you take magnesium oxide, right, and then what's going to happen? Those are the we want to know the ionic character. In this relation between magnesium and oxygen, you want to know whether it's purely ionic or purely covalent, or it's a mix between the two, right? So if we plug those numbers here in this equation, what's going to happen? We'll end up having 70.2% ionic. That means around 29 point something percent covalent, right? So it has, it's mostly ionic, but it has some covalent character. Okay, great. I think that will end the discussion here about the primary bonding, and I will stop here. If you have any